Hello and welcome back to Data Analysis and Visualization. I'm Jivita Christie, and in this video, I'm going to talk to you about combinations, which is continued from the previous video where I talked about permutations. And we are also going to talk about Bayes' theorem, which is a very important conditional probability theorem in statistics. So let's begin. Now, why are combinations important? So first of all, what you see here in the table is on the one hand, there are combinations of 1, 2, and 3, but there you can see that the order matters. So in that case, the combinations 1, 2, 3 and 1, 3, 2 and 2, 1, 3, all those combinations are different, are considered different. But when you're talking about orders, the order does not matter, then it is just 1, 2, 3. You do not have to list out the other things. So this is what we call combinations. And the other thing that you see is what we call permutations, which we saw in the previous video. Now, combinations are solved in this manner. So if you have the formula for combination is n factorial divided by r factorial into n minus r factorial. And this is just slightly different. The formula is slightly different from permutations because you just added that r factorial in the denominator, which wasn't present in permutation. So this is the formula, n factorial upon r factorial into n minus r factorial. Now, in the previous video, if you noticed, we took an example of marbles, that there were 16 balls or marbles available in the pool, and you wanted to pick 3. So how many combinations are possible? And at that time, we were talking about permutations, different permutations of that. And that's why we did 16 factorial upon 13 factorial, which I think gave us 3380. But now we are talking about combinations, which means it does not matter whether you picked first 1, then 2, and then 3. All that matters is you picked 1, 2, and 3. So how would you calculate it now? So in this case, 16 factorial upon 3 factorial into 16 minus 3 factorial, which results in 560 different combinations. And you can see this is much less than what we got in permutations. In permutations, we got about somewhere around 3,000 to 4,000, but here we are only getting a 3-digit answer because the number of possibilities are considerably reduced since we are now only talking about combinations and not permutations, and order does not matter. So this is where, suppose you do not consider the order, if you do not want to know the order, then this is how combinations are given: r plus n minus 1 factorial upon r factorial into n minus 1 factorial. Now we are going to talk about a different kind of probability, which is known as joint probability. So a joint probability is the probability of 2 events occurring simultaneously, which means when event A is occurring, at the same time event B is also occurring. So this is joint probability. It is denoted by P of A and B. The next type of probability we are going to discuss is known as marginal probability. So marginal probability is the probability of an event irrespective of the outcome of another variable. So for example, if you were to pick a card and wanted to find the probability of whether that card is red or it's queen, then that probability would be P of red and queen, which would be 2 by 52 in this case, because there are 2 red queens, one is of hearts and one is of diamonds. So the probability is 2 by 52. So this is where event X is equal to A for all outcomes of event Y. This is known as marginal probability. The next type of probability we are going to see is conditional probability, which is the probability of one event occurring in the presence of a second event. So for example, if you pulled a black card from a deck of cards, then what is the probability of this card being a 10? So a black card could be either spades or clubs. So what is the probability that it's going to be a black card of 10? So in this case, this is slightly different because we are already told that this card is going to be a black card. You picked a black card. Now what is the probability that this card is going to be a 10? So to do this, first we have to find out how many black cards are there in a deck. So there are 52 cards in a deck. Out of those, 50% are black, 50% are red, which means there are 26 black cards. So we are not going to calculate probability out of 52, but out of 26. So out of 26, the probability is, you can get two. You can get two black cards, two cards of 10. One can be a 10 of clubs, and one can be a 10 of spades. So that way you have a probability of 1 by 13. So this is conditional probability, which is denoted like this. It is known as P of A given B, which is denoted in this manner using a pipe between A and B. Now let's talk about independent events. Independent events are events that do not depend on each other. For example, if I'm going to go out today, then would I be carrying an umbrella? I would be carrying an umbrella if it was probably raining outside or there's a possibility of raining outside. Then I might take my umbrella with me. So that is a dependent event. Me carrying an umbrella is dependent on whether or not it's raining outside. So independent events are events that do not affect each other. So for example, if I'm going out, would I be taking something? Would I be taking my phone with me? That does not depend on whether it's raining outside or not, because I could carry my phone in my pocket. So these two events, me carrying my phone outside and whether it's raining outside, these two are independent events. So now we're talking about independent events. When two events A and B are independent, then what is the joint probability? The joint probability A and B is simply probability of A multiplied by probability of B. So this is your product rule in application. What about marginal probability? Now, marginal probability is where one event is dependent on another. And if we are talking about independent event, then the probability of A is just equal to probability of A. You don't have to worry about anything else affecting A. And what about conditional probability? So in the case of conditional probability, since we are saying that A and B are not dependent on each other, so it won't matter if B is occurring or not. Conditional probability is A given B. So B has already happened. Now what is the probability of A? So in this case, it's going to not affect the probability of A in any way. So P of A given B is simply P of A because B does not matter since A does not depend on B. And now we are going to move forward to Bayes' theorem, which is a very important theorem. And first, I'd like to explain to you what the theorem is about. So Bayes' theorem describes the probability of an event based on prior knowledge of conditions that might be related to the event. And to understand it better, let's take an example. So if cancer is related to age, then using Bayes' theorem, a person's age can be used to more accurately assess the probability that he or she has cancer. than can be done without the knowledge of the person's age. What that means is, does age matter while finding if a person has cancer or not? So this is where Bayes' theorem comes into picture. Bayes' theorem will let you find out if age affects the test for cancer. Okay, so should you consider age while testing somebody for cancer? Does that help you to get a more accurate result? So that is what Bayes' theorem is about. If age helps you to make your probability accuracy more, then you should use age by using conditional probability, and that you can do using Bayes' theorem. So that's what you'll learn in this theorem and these formulas that follow. So this is the Bayes' theorem formula. You can see here P of A given B is equal to P of A and B divided by probability of B. So this is a joint probability on top, and below that we are talking about only the probability that B will occur, because B is the event that occurs first, and then because of B, what's the probability of A? So that is your Bayes' theorem. And now we are going to see a practical example of the Bayes' theorem. So let us say this is a practical example. So this is some statistical data. It's not something that's just taken, that's just randomly written. So now 1% of women have breast cancer, which means 99% of women do not. And the test which is done to detect this type of cancer is known as a mammogram. So 80% of mammograms, they detect cancer correctly. And that's why 20% of them are wrong. So that means mammogram, the accuracy of the mammogram is 80%, which means 80% of the time when the mammogram says the person is having cancer, that means the person does have cancer. But 20% of the time they are wrong. Now, 9.6% of mammogram report cancer being detected when it is in fact not present. So this is a false positive. This is not as simple as 80% mammograms saying it is cancer, but it is not cancer. Now what we are talking about is a false positive. So false positive is where the report says that the person is having cancer, but the person does not actually have it. That's a false positive, which is 9.6%. And this is a simple table created based on those values that we saw. So what you see here in this table is a positive test. So if the mammogram reports that the test is positive, then the possibility of getting cancer is 80%, but the possibility of not having cancer is 9.6%. Now, if the mammogram report is negative, then the possibility of still that being cancer is 20%, but no cancer is 90.4%. This is the table generated from the data we saw previously. Now we will see how the Bayes' theorem example helps. So let us suppose that there is a person X who tests positive for breast cancer. So in this case, the table that you have, you are going to be using the positive row, the row that shows positive test. So that is the row that you're going to be considering because we are talking about a positive test. Now using that, we want to find out what is the possibility of getting cancer. So in this case, probability of a true positive, which means X has cancer and the result also was positive, is 1% into 80%, because 1% is the possibility of anybody having cancer. So 1% into 80%, which is 0.0008. and probability of a false positive, meaning X doesn't have cancer, but the result was positive. This is 99% into 9.6%, which is 0.09505. So 99% because that's the possibility, that's the number of people who do not have cancer. And 9.6 is a false positive probability. So this is the result of that. Now this is how the actual calculation is done. So probability of the person X having cancer, given that the test was positive, is equal to whatever we calculated just now, which is 0.008. Divide that by 0.008 and subtract from there 0.09, which we calculated, which comes to about 7.8%. So this is the probability that a person could still be having cancer, given that the test was positive, based on this table that we created. And that is how Bayes' theorem works in practice, and we'll be using this in our analysis in analyzing the data better by using this type of a conditional probability theorem. So that's it for this video, and I also conclude probability here. In the next video, we are going to start talking about what is inference in statistics. So remember the big picture that we talked about earlier. Now we are going to see what inference is, which is the last step of our statistical journey. So I'll see you in the next video. Thank you for watching.